and then also scattering factors. And we'll learn all about these four items when we talk about X-ray diffraction after uh, the midterm. And then we have data processing. We'll go through this as well. So once you collect the data, you have to process it. It's referred to as integrating data. And then we apply different what we call absorption corrections to the data. And this again, this will be after uh, the midterm area when we start looking at solving crystal structures. Symmetry determination. So once you process your data, you're going to have to determine the symmetry of the data, and that tells us, for example, which crystal system it's in, its lattice parameters, is there any centering, and then also based on what we call systematic absences, we can determine the space group for that crystal. Now, some of this stuff we'll be looking at next week. For example, centering, symmetry operators, space groups, but the applying it to what we call systematic absences will be in the second half of the semester. And then lastly, with the crystal structure, we have structure determination, which we'll spend a whole week on. And there are many different methods you can employ through OLEX to solve the initial starting point of your structure. And then you refine it. And once you refine it, you can interpret the crystal structure. So when we solve a structure, the first thing you do is you use, for example, what's called the Patterson method or direct methods, and it gives you an initial starting point for you to go in and solve or analyze your structure. So for example, just imagine if you have a map, and on the map it labels a few of the roads that it knows, like major highways, and you have to go in and label the side streets in the city. The same thing with when you're solving a crystal structure. When you use one of these methods, if you have heavy elements, it does a good job of locating those, but sometimes you may have to go in, once you know the heavy elements, you have to go in and identify where the light elements are in the structure. So that's kind of an overview of the path to getting a crystal structure for a sample. So again, the most important thing is crystal growth and selection. You have to select a good crystal in order to get good data, because if your crystal's bad, you might as well, it's not worth the hassle. So today, again, we're going to be talking about these two, X-ray generation and X-ray detection. So why do we use X-rays? Because you can think of, if we remember when we talked about unit cells or crystals, they contain very small diffraction gradients. And the only way to penetrate these small spaces between the planes of atoms in the crystal is by using a type of, I guess you could call it light or electromagnetic radiation that can penetrate it, would be X-rays, because it's small enough wavelength that it can penetrate between the different spaces between the atomic planes in the crystal. Now, we can't really use a microscope because again, it's smaller than what we can see from a microscope. And so that's why we use X-rays to analyze crystals, and because it's a higher resolution type of radiation than visible energy. And so when we use X-rays, you can kind of think of it as a X-ray microscope. So we're using X-rays to see what's beneath the surface of the crystal. Just like with a microscope, you use light to see what's inside the specimen of the frog or what's inside cells. So you can kind of think of it as a X-ray microscope. Now, the one thing that is different between X-rays and light is, for light, when you have a microscope, you can recombine and magnify the light by using lenses. However, when you talk about X-rays, you can't magnify the intensity of an X-ray by using lenses or magnification. The way you have to recombine intensities for X-rays is by, as we'll see later on, is by geometry and mathematics. So you have to use equations in order to recombine the individual intensities that are shown. And so when we measure the difference in intensity of the X-rays, we have to provide a fixed wavelength. So when we're producing X-rays, we have only one wavelength that we use. So the wavelength is fixed, and then we can diffract the X-rays on the crystal, and then from that we can measure the difference in intensity of the different diffraction spots. So when we use X-rays, as we'll see in just a little bit, we only use one particular wavelength of X-rays. And you'll notice that when we generate X-rays, we generate multiple different types of X-rays. So some of those will have to be filtered out so that we only get the characteristic X-ray that we're looking for. And so X-rays were first discovered by William Roentgen, and they were called Roentgen rays. And the reason they used the word X is because back then they didn't know what exactly an X-ray was, so X signifies as an unknown. So they had these unknown rays that were emitted from a Crookes tube, which is a cathode ray tube, when they applied voltage to a particular barium compound that fluoresced. And it wasn't until 1901 that Roentgen won the Nobel Prize for these new kinds of rays. Again, they didn't know exactly what they were, so that's why they used the letter X to signify some type of unknown ray was produced. And they originally this was used to show photoabsorption. So for radiology, you take X-rays of bones. You can see if a bone is broken, whatnot. It wasn't until a little bit later with Max von Laue that they showed that X-rays can be diffracted by crystals. So the main initial use was for medical purposes in the like radiology. And there are two classes of X-rays. There are soft X-rays and hard X-rays. And so X-rays have a range between 100 electric volts to 100 kilo electron volts. And the two types of X-rays are soft X-rays, which are your lower energy, longer wavelength X-rays. So longer wavelengths means it has a wavelength of longer than 2 angstroms. And then there are hard X-rays, which are the higher energy X-rays, and these are less than 2 angstroms. And so for single crystal analysis, we use the hard X-rays. You'll see that the wavelength, for example, for copper is 1.54 angstroms. So if we have copper source, the X-rays produced are about 1.54 angstroms. And for molybdenum source, and we'll show you what the source is in just a second, it's about 0.71 angstroms. And these are the two most common sources that we use to produce X-rays, and you can see their wavelengths are less than 2 angstroms, indicating that they are hard X-rays. So they're very high energy X-rays. And so the thing with X-rays is they travel in straight lines, and they can, when they strike a photographic plate, they darken the plate. And they use photosensitive paper to show where these spots form when the X-rays strike after being diffracted by a crystal, or when they shine X-rays onto, for example, a hand. It darkens the photographic plate behind it where the X-rays were absorbed, and that's where we get the characteristic X-ray picture. Again, this is around the beginning of the 20th century. And so the next obvious question is, how do we generate X-rays? And there are two ways you can generate X-rays. One is using radioactive isotopes, such as iron 55. But for X-ray diffraction experiments, this is not ideal because it has a very low flux. So it's not it's not ideal for X-ray diffraction experiments. So we don't use radioactive isotopes. What we use are high energy electrons to produce X-rays. And so what we do is we accelerate these electrons, and then they collide with the valence electrons in an anode target. And when they collide with these electrons, they remove an electron from the anode, which we'll talk about in just a second. And then when an electron comes from a higher energy state, relaxes down to the lower energy state, it releases an X-ray. So you have electrons that come in, they strike an electron in a lower energy level, it ejects that electron, and then an electron from a higher energy level falls down and occupies that void. And as it falls down, it releases a photon, which is in this case, an X-ray photon. And that's how we use electrons to make X-rays. So we have a high voltage filament. It's kind of like, you can say, a very high voltage light bulb. So instead of producing light, when you pass electricity through the tungsten filament, it excites the electrons, you produce light. But here we have a high voltage. We pass through a filament. It produces electrons. These electrons accelerate toward a metal target. And the target is what we call the molybdenum source or the copper source. And as it strikes that target, it ejects electrons. And at the same time, electrons fall down to the lower energy levels. And as they do that, they release a photon of X-ray. And as you can imagine, there's lots of electrons hitting this, what we call anode target. So you get lots of different photons being emitted. But as we'll see in just a little bit, there's only one type of photon that we're interested in. And that's why we have to, as you want to say, filter the rest of the photons out. Now, this type of system produces a lot of heat. So it has to be cooled with cooling water. They're not air cooled because it gets hot really fast. And if the cooling water doesn't work, from my experience, this happens a few times. It shuts off almost immediately because it gets too hot to run. Now there are types of targets. So the anode target can be stationary, or it can be a rotating target, so that when it rotates, this anode target, it evenly distributes the electrons. So sometimes the target rotates, sometimes the target is stationary. And we'll show you this diagram in just a second. So again, we use electrons, high energy electrons, to produce X-ray photons by striking what we call an anode target, which is a metal. It strikes the metal surface. As the electrons hit other electrons in the metal, they get ejected, and then you have this cascading effect where an electron from a higher energy orbital falls down to the lower energy orbital to occupy that empty orbital, and in the process removes an X-ray photon. So this is a kind of a diagram to help you visualize what's going on. So we have over here our high-speed electrons, and again, these are produced by some type of filament. So and it's a very, when we go into the X-ray lab, I'll show you there's a very thick voltage cable that plugs into the back of what we call the source. It produces hundreds of thousands of volts to make these high-speed electrons. So these high-speed electrons come in, they can do one of two things. They can come in and they knock an electron out of what we call the first energy level, or commonly referred to as the K shell. So if you remember back in Gen Chem 1 when we talked about quantum numbers, the energy level was referred to as the number. But they also have capital letters that denote the energy level. So K shell refers to the first energy level. And then the second energy level is referred to as L shell. And then after that, it goes with M and so forth. So L shell, N equal 2. And so this K and L shell tells you which shell the electron was ejected out of. And so what happens is we have a high-speed electron. It comes in, it kicks out an electron from, in this case, the K shell, and then an electron from a higher energy level, in this illustration, the L shell, comes down and occupies the empty slot from the ejected electron. And in the process of relaxing back down to the first energy level called the K shell, it releases a characteristic photon, which is our X-ray photon. Now you have to imagine that this is a cascading effect. So when this electron in the L shell comes to the K shell, now the L shell is unoccupied. So then an electron from the M shell goes to the L shell, releasing a photon, and then that M shell is now unoccupied. So then an N shell goes to the M shell. So it keeps this like a chain reaction until all the electrons occupy lower energy levels. So you get all these different photons that are produced. So this is one way a high-speed electron can create X-rays, is by ejecting a lower shell electron, causing an upper shell electron to occupy. And as it comes back down to the lower energy state, it releases a characteristic X-ray. So those are called characteristic X-ray photons. And lots of these can be produced because it has a cascading effect. The other thing that can happen is you have a high-speed electron. It comes near the nucleus. It slows down, releasing some of its energy. As it releases its energy, it's X-rays, but it's not a characteristic X-ray. It's like a continuous spectrum of X-ray photons being emitted. So, and this is a weird name. It's called Bremner-Strahalung X-ray photons. And you can think of this similar to a if you go to the stove and you turn on the stove, you heat up the stove element, it gets hot. When you turn it off, even though it's turned off, it still radiates energy because it still radiates heat from the stove element. This is similar to what Bremner-Strahalung X-rays are. So as the electron passes near the nucleus, it releases some of its energy. The energy is emitted as a continuous spectrum, so it just emits the X-rays, just like a stove when you turn it off still emits heat. So it's not one particular wavelength, as we'll see in a little bit. It's over a broad range of wavelengths. That's why we call it similar to what's called a continuous spectrum. So the high-speed electrons can do two things. It can interact with electrons in the anode target, or it can interact with the atomic nucleus. What we're interested in is the electrons that interact with the electrons in the anode target, not the nucleus. So characteristic X-rays are what we want. But we produce both these types of X-ray photons. So now how do we get X-rays? Just to kind of show you the difference, we have Bremner-Strahalung, which is as it goes near the nucleus of the atom, it releases X-rays. And then we have the fluorescence, which is when the primary electron interacts with an electron in the atom, causing X-rays to be produced. And so Bremner-Strahalung, again, the electron from our filament comes in. As it slows down, as it gets near the nucleus, it emits an X-ray. And Bremner-Strahalung, if we look at this spectrum in the lower right-hand corner, it's this broad hump. So it ranges from about 0.04 nanometers to 0.12. So it's kind of like a continuous spectrum. So there's not one characteristic wavelength for Bremner-Strahalung X-rays. It's a continuous. So it means it has a range of wavelengths. That's what Bremner-Strahalung X-rays are. The other one is fluorescence, and this is what we're interested in. So you have an incoming high-speed electron. It hits an electron in one of the energy levels of our metal target. It ejects that electron, and then an electron from a higher energy level occupies that lower energy level, emitting an X-ray from it. And those X-rays that are emitted are discrete wavelengths. So this is what we call the K beta X-ray, and this is the K alpha X-ray. So these are discrete wavelengths photons. So they have a particular wavelength associated with it. And we'll talk about what the K alpha and K beta mean in just a second. But the main thing here is to note that Bremner-Strahalung incorporates a variety of different wavelengths. So it's not just one wavelength. It's like a broad spectrum of wavelengths, whereas fluorescence, depending on what electrons move, we get discrete wavelengths. So K beta, for example, has a discrete wavelength. K alpha has a discrete wavelength. And so those are the types of X-rays that we want to analyze crystals. We want the discrete ones, not the continuous emission. Now, when you have a chance later, check out these two links here. It shows you the difference between the Bremner-Strahalung and characteristic X-rays in a little video. So now we're just going to focus on the fluorescence and how they produce different X-rays. Again, we're not too concerned about Bremner-Strahalung because we don't use that in X-ray crystallography. We use the discrete wavelengths. So as we see here, we have a high-speed electron comes in. It's going to knock out an electron from an energy level, and then an electron from an upper energy level cascades down, releasing an X-ray. So let me tell you what some of these things mean. So for example, K alpha and K beta, the K represents the energy level that the electron went to. So whenever you see K alpha or K beta, that means an electron from a higher energy level fell down to the first energy level. Now alpha means it only moved one energy level. So K alpha means that it went from the L shell, the electron, transferred from the L shell to the K shell. So alpha means that the higher energy electron fell from an energy level that's one above the K level. So K alpha means that an electron from the L shell moved down to the K shell. So since it's only one energy level difference, it's referred to as alpha. And then we have beta, and beta moves down two energy levels. And so here K beta, electron goes from the M shell to the K shell. And of course there are other ones as well, so you could have it from the N shell to the K shell, but alpha and beta are the two most common types of electrons that have very close wavelengths. And then you'll see that for L alpha and L beta, L again means that the electron falls to the L energy level. Alpha means it's a difference of one energy level, and beta means it's a difference of two energy levels. Now, the way this shows up on a spectrum, This here that you see underneath, this is that Bremisch-Straha lung. I'll say BSL. So all of this absorption here that you see at the very bottom is due to the Bremisch-Straha lung X-rays. Now what we're interested in are the specific wavelengths where we see X-ray photons. So you see here we have K beta, we have K alpha, and you'll notice that it's K alpha 1 and 2. And we'll talk about what the difference between 1 and 2 is in just a moment. And then you over here to the far right, you see we have L beta and L alpha. So it's very easy to not include L beta and L alpha because it's further to the right. So it's very easy to filter out the L beta, L alpha radiation because its wavelength is very different from K alpha radiation. So in X-ray crystallography, we use the K alpha radiation, K alpha 1, and we use K alpha 2. We do not use K beta. Now for copper source radiation, the K beta is very close to the K alpha. So what you would have to do is you would need to filter out or account for the K beta radiation so that you can remove the intensity due to K beta out of your data. Because we're only interested again in K alpha is the characteristic X-ray that we want. We don't want K beta, and with most X-ray diffractometers we have beta filters which filter out the K beta, so we don't need it. If you do include it, it's going to throw off your intensities because instead of just being K alpha 1, K alpha 2, you're going to include the K beta. So it's going to make your diffraction spots more intense because now you have more X-rays striking the crystal. So for X-ray crystallography, we're only interested in the K alpha radiation. And we'll talk about what alpha 1 and alpha 2 are in just a moment. So those are the characteristic X-ray photons. So here we're going to look at the difference between K alpha and K beta. This goes to, if you've taken inorganic chemistry, you might have looked at these types of diagrams before. And so it's not as simple as looking at if you remember a few slides back, we had a Bohr model representation of the copper atom, and we showed the N equal 1, N equal 2. That's not a very good, I would say, representation of the electronic levels in an atom. And these diagrams do a better job at representing the electronic levels in the atom. Now, some of these transitions are what we call, not valid, they're called something. Some of these transitions are allowed, some of them are forbidden. And when you take descriptive inorganic, or I believe in inorganic chemistry, you'll talk about, which of these transitions are allowed and which of these transitions are not allowed. Just to give you a little bit of introduction to these types of diagrams, when two atomic levels differ by one quantum level, then the transition is described as alpha lines. So you see here, L3 is a 2p orbital, L2 is a 2p orbital, and then it falls down to the 1s. And so here, 2 minus 1 means there's a difference of 1 in the quantum number. So we have 2 minus 1, a difference of 1. So those are allowed, and they're called alpha transitions. Notice that, for example, the 2s, there's no transition from, because there's 2s to 1s, I believe, is a forbidden transition. But you'll learn about these when you take inorganic chemistry. So alpha means that there's a difference of 1 in the principal quantum number. So 2p to 1s. So remember that the second energy level has a 2s orbital and a 2p orbital. And remember that the 2p is higher in energy than the 2s. And so that's why there's a transition from the 2p to the 1s, because in the second energy level, 2p is higher than 2s, so he's going to always remove from the higher energy orbitals first. And so k alpha 1 is from the 2p 3 halves level, and k alpha 2 is from the 2p 1 half. And if you notice on the previous slide, let me just go back because this is pretty cool. Let me go backspace. So notice here, so the energy gap of k alpha 2 to k alpha 1, or to k alpha 2 to the first energy level, is smaller than the energy gap from Ka1 to 1s. And you'll see here that K beta, or K alpha 1, let me go back. So see, K alpha 1 has a shorter wavelength than K alpha 2. And if we go here, we go forward, notice that the energy gap of K alpha 2 is smaller than the energy gap of K alpha 1. So remember, if you can refer back to Gen Chem 1, you'll remember that the smaller the energy gap, the longer the wavelength. So here we have K alpha 2 to the 1s orbital is smaller in energy, therefore it has a longer wavelength, whereas K alpha 1 has a larger energy gap, and it's not much larger, but it has a shorter wavelength. So if we go back to the previous slide, you'll see that K alpha 1's wavelength is shorter than K alpha 2. And then K beta is a big energy gap, and that's why K beta is further to the left. It has a very short wavelength compared to K alpha. So again, the energy gap, you can kind of get a reference of where the wavelength will be. So that's why we have 2k alphas, because the 2p orbital splits into 2p 3 halves and 2p 1 half. And you get both transitions. And you'll learn more about these diagrams in inorganic chemistry if you take that course. But I just wanted to show you that's where the K alpha 1 and K alpha 2 come from. And we don't filter out the K alpha 2 from the K alpha 1 because they're so close together, you can't filter. So we adjust the mathematics to account for the weighted percentage of K alpha 1 and K alpha 2. So it's kind of like they're weighted based on their relative intensities. But we can filter out K beta because it's further away to remove it. This is just more of an elaborate diagram so you can see the difference. So even L alpha and L beta. So if for L, we have actually multiple betas that can happen: L beta 1, L beta 2, or 4 and 5. And actually, these are actually here. This is the selection rules to show that these are allowed transitions. So the change in N has to be non-zero. So to be a allowed transition, you can't go from, say, you can't go from N equal 3, L equal 2 to N equal 3, L equal 1, because there delta N would be 0. That would be a forbidden transition. The difference in L has to be plus or minus 1. So that's why, for example, you don't have a transition from L equal 2, or no, excuse me, N equal 2, L equals 0 to N equal 1, L equals 0, because the change in L is not plus or minus 1. So those are forbidden transitions. So what you're seeing here are the allowed transitions based on these rules here. The change in the J value has to be either plus or minus 1 or 0. So for example, you couldn't go from, for example, 3 and 7 halves to 2 and 3 halves, because there the difference in J would be, what's that, 7 halves minus 3 halves would be 2. So that wouldn't be an allowed transition. So that's why some of these you don't see transitions, because they're forbidden by these selection rules. Again, you don't have to memorize, just know that some of these are forbidden because of these selection rules. Here, it has to abide by this set of rules in order to be an allowed transition. But also note that we get a variety of X-rays that are produced. So it's not just we get K alpha 1 and 2, we get K alpha 1 and 2 and all this other set of photons as well. So when it comes out of the source, as we'll see in a moment, you got all these different wavelengths of photons beaming out of the source. So we have to use some type of filtering to remove the stuff that we don't want. And so we need to use what's called beta filters to filter out the K beta radiation, so that we only get a one type of wavelength photon that passes through. And so beta filters can be a variety of different metals. It depends on what type of anode target you're using to produce your X-rays. For example, here, if you notice, we have K alpha 1 and 2 shown here, and down here, this is the K beta. And this is for copper, actually. If we're looking at it, I believe this is copper radiation. So the anode target was copper, and you'll see that this, well, so copper filter and a nickel filter. You'll notice that when we use a nickel filter, it blocks out the absorption due to the K beta radiation. So if you were to set up a filter for this type of radiation, you would use a nickel filter, because you see here its absorption covers the K beta wavelength. And so that's why we use particular metals to filter out the K beta, because we don't want the K beta to show up in our diffraction pattern. Now, if you don't align the filter correctly, you can have the K beta show up. So you have to make sure you adjust the filter so that it covers the K beta wavelength. And so there are a variety of different filters. So if your target anode is chromium, we use a vanadium filter. Now for us, we mainly use copper and molybdenum targets. And since we use those, our filters are usually nickel and zirconium. And you'll see that a nickel filter removes 98% of the K beta radiation for copper. And for molybdenum, zirconium removes almost 99% of the K beta radiation. So we use these filters to remove the K beta radiation, so that we only have the characteristic K alpha radiation. And that's what we want when we're doing X-ray crystallography. We want the K alpha. Again, the target is the metal that we use to strike high energy electrons to produce the characteristic X-rays. And I'll show you, I know I've been saying I'll show you, but it's coming up, the example of a target here. So the targets are metals that the high energy electrons strike to emit X-rays. And then the beta filter removes the K beta X-rays from it. And down here, just to show you that they also use niobium as a beta filter for molybdenum as well. So we use beta filters to remove the K beta radiation, but we also have to use a monochromator to adjust it so that we can have only the K alpha radiation to pass through. So you have your source that produces all these different types of X-rays. We adjust what's called a monochromator, which usually contains a filter on it to remove the K beta, and we adjust it so that it only allows a particular wavelength to pass through. And so here you can see that we have K beta, or excuse me, K alpha 1 and K alpha 2 that's allowed to pass through. And what they do is, to get the adjusted K alpha wavelength, they take the wavelength of K alpha 1, K alpha 2, and do a weighted average of the two, and that's where they get the wavelength K alpha star. This is very similar to, if you remember from Gen Chem 1, when you're calculating the atomic mass of an element, you would take the atomic number of, oh no, it's atomic number, no, the, not atomic number, the mass number of each and multiply it by its percent abundance. This is similar to that. So you take the wavelength of K alpha 1, multiply it by its weighted value, so maybe it's 90% K alpha 1, 10% K alpha 2, and then you would get the weighted wavelength. So it's weighted against K alpha 1 and K alpha 2. And so we mainly use copper and molybdenum. So copper has a characteristic wavelength of 1.5418, and molybdenum is 0.7107. And so we use the monochromator to adjust it so that it only allows, for example, if it's copper, it only allows 1.54 K alpha radiation to pass through. And then if K alpha 2 is too close together, such as in copper, there's computer programs that can remove the K alpha 2 from it when you're integrating after data collection. Most of the time it's included, and it's a weighted average of the two. So we have a source that contains an anode target, which is a particular type of metal where high energy electrons strike that produce a variety of different types of photons. Then we use a monochromator and a beta filter to remove the types of radiation we don't want, and we're only interested in the K alpha photons, and that's the ones we want to allow through to strike the crystal. Now, once you get through the monochromator, we have our K alpha radiation. But when it's coming out of that monochromator, the X-rays are going in all different directions. So what we need to do is we need to have something that can focus the X-rays into a coherent beam. And so what we use is something called a collimator. So a collimator kind of focuses the X-rays when they're coming out of the monochromator so that they produce a uniform beam to strike the crystal. And it's the collimator that dictates the size of your crystal, because the collimator is what sets the size of the X-ray beam that strikes your crystal, that strikes the crystal in your diffraction experiment. And there are many different types of collimators. You can have 0.3, 0.5, and 0.8 millimeter collimators are common ones. So if we use a 0.3 collimator, what that means is that our crystal cannot be bigger than 0.3 millimeters in any direction. So we have to cut the crystal in order to fit inside the entire beam. So we don't want a crystal that is bigger than the beam, because not all of the crystal will be hit by the beam. And so I don't have a picture of one, but on next week I'll show you what a collimator looks like. It's actually a kind of a cone shape tube that kind of filters or aligns the X-rays into a uniform beam that can strike the crystal. So for us, we have two X-ray machines. On one of them we have a 0.5 collimator, and I believe on the other one it's a 0.3 collimator. So on the older machine you can use bigger crystals, but on the newer machine you have to use smaller crystals because we have a smaller, more powerful beam. So you have your source that produces the X-rays because it hits that metal target. You have the monochromator with the beta filter that only selects the K alpha radiation. Then you have a collimator that kind of puts all those K alpha photons into a uniform beam, and now you're ready to strike the crystal with your X-rays. And a collimator looks something like this. So what you have is you have the X-rays coming in. They're going in all different directions. But when they get into this tube, they kind of uniformly form a beam. And then the beam comes out and strikes the crystal like that. So that's a collimator that is needed. So now we're going to talk about how we produce these X-rays. And so what we have are two different types of what we call a source, and a source is referred to as where the X-rays are produced. So this is referred to as a source. And the source is usually in reference to what type of anode is used. And there are two main types of sources we use. We use the copper source, which has the 1.54 angstrom radiation, and the molybdenum source. So for small molecules, these are the two most used sources that we use. And just to give you an idea, if I was to comment on the power of each one, copper source you could think of as a big bodybuilder, very strong, powerful beam. Molybdenum source you could think of as a, I don't know if you ever watched, what was that? There was this cartoon, not cartoon, Peter something. He was I don't know, he was a comedian. But anyways, kind of a weak, lanky kind of person. You know, moly source is not as powerful as copper. When you use a moly source and you run the same crystal on a copper source, moly source is like driving a school bus. Copper source is like driving a Ferrari. So there's two completely different types of sources. I mean, copper is more preferred if you have it because you can do faster data collections because it's a stronger source versus molybdenum. So on one of our instruments, we have a copper source, and on one of them, we have a molybdenum source. And so these sources are in what's called a sealed tube. So a sealed tube is like a big fancy light bulb that we use to produce the X-rays. So what happens is over here, we have a very high energy plug that plugs into this tube. So imagine you plug it in, it's like 100,000 of volts. And we have this cathode filament, which is typically tungsten. So this high energy comes in, it excites the tungsten filament and produces X-rays. The X-rays strike the anode. So the anode here is what's referred to as the copper source or molybdenum source. It's the type of metal that the electrons strike. And so again, we use mainly either copper or molybdenum. So when the electrons strike the anode, it produces X-rays. And these X-rays are going to be produced perpendicular to the incoming electrons. So whenever you see an X-ray diffractometer, the source is always perpendicular to where the X-rays come out. So as the electrons from the filament strike the target, it produces X-rays, and they go out through what's called a beryllium window into the monochromator. So this X-ray beam here would then pass through the monochromator to only select the K alpha radiation. So again, the tungsten filament produces the high energy electrons that strike the anode target, which produce the characteristic X-rays that go into the monochromatic. And it is a vacuum sealed tube. Older tubes are about 2 to 3 kilowatts, and our newer machine, it's not kilowatts anymore, it's like 50 watts or something. It's ridiculous, but it's more powerful. It's a stationary target, so this anode target doesn't move. So one of the disadvantages is that high energy beam of electrons from the filament is always striking the same part on the target because the target doesn't rotate. It has to be cooled because as those electrons are striking that anode, it gets very hot, so you have to cool it, and then the X-rays pass through the beryllium windows. And next week I'll show you what an actual sealed tube looks like. This is just showing you more of a characteristic cartoon of what happens. So here we have an AC current, which is the high energy plug that you plug in. So there's actually a power supply hooked up to the X-ray diffractometer that produces this high energy voltage, and the filament produces the electrons that strike the surface of the anode target, in this case copper. And then you see that the X-rays that are produced are going to be roughly perpendicular to the target. And so whenever you see the setup of a X-ray diffractometer, the source, which contains the sealed tube, is always going to be perpendicular to the monochromator, which allows only the characteristic X-rays to pass through. And again, the typical metal for the cathode is tungsten. So this is just kind of explaining what it does. It does thermonic emission. So it produces the high energy electrons. They eject electrons and then they make X-rays. Just and show that it's perpendicular. The X-rays are perpendicular to where the electrons strike the surface of the anode target. So, one other type of source is a rotating anode, and the only difference between a rotating anode and a sealed tube is that the anode rotates so that you're not always hitting the same spot on the anode. Now this is a more powerful, or used to be a more powerful type of source, but it requires a lot of maintenance for it. The sealed tube is a very low maintenance device. It doesn't require any maintenance except changing out the tube when it burns out. But rotating anode requires a lot of maintenance and is very expensive. And secondly, it requires a bigger unit because the source has to be bigger. The whole diffractometer itself is bigger. They used to use rotating anodes, or maybe they still do, for protein crystallography because it's a very powerful device or source. Nowadays, though, there are certain national labs that use what's called synchrotron sources. And so synchrotron is like, I don't know, it's like a rocket ship compared to a Ferrari. So Ferrari was the newest top of the line diffractometer you can have in your lab. But synchrotron is like a rocket ship. So it's going to be more powerful, it's going to be faster than anything that you can have in the lab. And you have to submit these to national labs for data collection. So typically, these are for either macromolecules, proteins. So lots of protein crystals are sent to national labs to use synchrotron data. Or if you have very small crystals that are very poor quality, you can send them to synchrotron labs with synchrotron beam lines as well. So that's another type of, I guess, source that we can use, and it's very powerful. Like I said, it's like a rocket ship compared to a Ferrari. It's going to, you know, it's a very powerful machine. So those three methods are what we commonly use to produce X-rays. Now we're just going to spend a little bit of time talking about X-ray detection. So when the X-rays get diffracted by the crystals, there's going to be a detector on the other end that captures the diffracted X-rays. And there are things like point detectors, which are zero-dimensional detectors, linear detectors, which are one-dimensional, and area detectors, which are two-dimensional. And in our older machine, we have a what's called CCD detector. In our newer machine, it counts directly the number of photons that strike the surface of the detector. So we'll just spend a little bit of time just kind of explaining the difference in the types of detectors. So with point and linear detectors, these are mainly from the old days when they first started using X-ray detection. They take very long data collections because you can only look at a particular part of the crystal. So you have to rotate the crystal in different positions and the detector in different positions to collect the whole set of data for it. Nowadays, area detectors are more commonly used, and they even have curve detectors as well. So there's lots of advances in X-ray detection. So when they first started using X-rays, the detection was just photographic film. So the X-rays would strike the crystal, diffract, and then they would hit the photographic film and interact with the film to produce spots, diffraction spots. And from that, you can measure things like the cell geometry, the orientation of the crystal. But all of this was done visually. So they would have to look at each diffraction image and determine the geometry, the orientation of the crystal. Now, this is a permanent record, but it's not very precise, and it takes a very long time. Imagine looking through thousands of diffraction images and trying to determine the orientation and cell geometry of the crystal. It'd take a long time. Yeah. Now, what we use today are area detectors, and there are many different types of area detectors, but typically you have a surface, which is kind of an area, a screen where the X-rays hit. And this allows for a larger area to be covered when the X-rays are diffracted from it. And so what these area detectors have is what's called an imaging plate where the X-rays strike the plate. And so if we look down here in the lower left-hand corner, this is an example of a CCD setup. So you have this imaging plate here, which is called the phosphor. The X-ray photons strike the phosphor screen, and wherever it strikes, it produces, on the other side, visible light photons. So you can kind of see we're converting X-rays into visible light. So there's some conversion and there's some information lost in the conversion. And then the light that's produced on the other end is picked up by a fiber optic and read into a CCD, and you get your image popped up on the screen. So you see we convert the light, and then the light passes through a fiber optic, gets read in by the CCD, and then we get our diffracted images. And so every time it collects an image, this is what it did. The X-rays strike the surface, produce visible light photons, which is read by a fiber optic cable, then read into or travels through a fiber optic cable and then read into a CCD, charge coupled device. Now these have to be cooled, and due to the fact that you're converting X-rays into visible light, it doesn't have the best sensitivity, because you got to convert from one to the other. Nowadays, they have detectors that directly count the X-ray. So when the X-ray strikes the surface, it's read directly into the, I guess you could call it CCD-like system. So there's no loss in conversion, which makes it more sensitive instrument. But the older machine that we have at UTSA uses a CCD detector. So we convert the X-rays into visible light, travels through a fiber optic cable, and read into a CCD. This is just showing you again what happens. The X-ray photon comes in, and then it goes through, and then visible light comes out the other end. Oh no, this is a direct, so it's directly reading the X-ray photons as it comes in. So if you see the difference, direct means it reads the photon directly as it strikes the detector, the screen. And then we have indirect, which is what the older technology is, where the X-ray photon strikes, it produces visible light, and then it travels through the cable to the CCD detectors. That's what is indirect. Direct is more sensitive than indirect detector. And this is another type of CCD detector. So that it's just a light pipe taper, different way for the light to travel to the CCD detector. But again, the main thing is when the X-rays strike the imaging plate, it produces visible light, which is then read by the CCD detector when it's an indirect CCD. When it's direct, that means that when X-rays strike, the X-rays are read directly from the imaging plate. When it's indirect, you got to convert the light, and then the light is read by a CCD detector. So why do we use area detectors? Well, we can measure more data at once and at the same time, so it allows for faster data collections, higher resolution, and we can see more of the diffraction pattern rather than if we're using a one-dimensional detector, it's only a single location, more redundancy data. We'll talk about redundancy later on, but it's measuring data over the same set of parameters more than once so that you're seeing that this intensity is always in, for example, in this spot. It's not an anomaly. Higher resolution, which is always good. The higher the resolution, the easier it is to solve your crystal structure. So if you have low resolution data, it can become quite difficult to solve a crystal structure. So the way we use an area detector to collect data is we mount the crystal. We'll show you that next week. We do a few general screening. We call it screening. We do a few general images to identify the unit cell and its orientation. And this is important because based on the screening, you can tell if this is a good crystal or not. And it does this very fast. So the screening only takes about 10 minutes. Then once you do the screening, you can do a full data collection. So the crystal is actually rotated in half-degree increments while the X-rays are shining on it. So it gets kind of a scan of the crystal. It's not just one position. So the crystal actually moves usually a half degree while the X-rays are being striking the crystal. So, and then once we collect a variety of different images, we go then and integrate and determine the intensities of the different peaks. And again, we'll show you all of this. This is more when we go and actually start collecting data and integrating That's where these come into play. Now, the number of images collected depends on the type of crystal, its diffraction, how it diffracts, but it could go anywhere from 500 images, which contain thousands of data points, and I've had some where I've done like 2,000 images that contain maybe 50,000 reflection points on it. So with area detectors, you can do a lot more. You can obtain a lot more data than with the older detectors. And so again, with the crystal, it can be rotated about a unit cell axis, and you can assign HKL indices by looking at the diffraction patterns. And we'll talk more about HKL indices next week when we talk about Miller indices. So just to kind of give you an overview of what we just talked about, and then we'll finish for today. But we have a source. I know we covered a lot of information today. We have a source that produces X-rays. And then from the source, we have a monochromator. And this contains a beta filter. So the X-rays travel from the source to the monochromator. And then from the monochromator, it goes to a collimator. Where it's focused into a coherent beam. And then from the collimator, it strikes the crystal. And then from the crystal, it goes to the detector. And the detector displays the image on it. So that's kind of the flow chart of how the X-rays travel from the source to the detector. Now from the detector, what we do is just to kind of give you a prequel of what's to come. We have a diffracted image or images. From this, we determine unit cell and crystal symmetry. So you can determine the lattice parameters and crystal symmetry from the diffracted images. We then integrate and so integrate, what we're doing is we're assigning intensities to HKL values. And then once we integrate and assign HKL values, then what we do is electron density peaks are assigned in the unit cell. So imagine a map where nothing is labeled and you have to go in and assign the different streets, buildings, etc. And then once this is assigned, this is when you solve structure. So that's kind of like the process that we go through. So a lot of this we talked about the top part, going from the source to the detector, from diffracted images to solve structure. We'll do most of that in the second half of the semester, but just kind of give you an idea of this is the process that goes into solving crystal structures. So that's all I had for today. I'll go ahead and stop the share so we can, if you have any questions. And stop.